Hello everybody. Welcome to another video. I'm not really sure where I am right now. Some people keep talking about the Republic and what I have to do to help them stop the Empire. Whatever. I don't know. I don't care. Let's do some math, shall we? Alright. So far with this whole eigenvalue thing, I'm gonna take these off. We've done a grand total of one branch, is when both the eigenvalues were real, they were distinct, and they were not zero. And today we're going to do a separate branch, and we're actually going to cover both of these bad boys here when it's complex, either purely imaginary, like the bottom case, or that it has a real part, the top case. Alright, there's a lot to go through here, and I'm actually going to do it in a very different way. I'm going to try to borrow from the lessons we learned from second order differential equations, okay? And what you should recall is that any second order differential equation is the exact same thing as two-dimensional first order differential equation system. If you don't remember that, go look at one of the videos that we've got in the previous on the thingamajigger, what's it called, playlist, and also I have that extra which shows how to definitely go back and forth through this as long as they are linear. That's the important part, okay, is that we have linear differential equations here. All right, but we're going to exploit that a lot, and so to do that, because we studied our butts off with second order differential equations of the form x double prime plus px prime plus qx equals 0. Okay, so the important thing here is that we are linear, we have constant coefficients, and we're homogeneous, so it's not forced. Do you remember how to solve these? I certainly hope so. Okay, we're going to be using the ansatz solution, right? Which leads us to the, what's it called? The characteristic equation. Okay, that's going to be the important parts that we're going to focus on for solving them. But first, let's take another step back at modeling, okay? Specifically here, we've got these two terms. We've got px prime and we have qx, and I would really love to remember what the heck these things mean in the context of what does this equation mean. All right, I want to use the entire equation to represent a mass spring. This is going to be the thing that we're remembering. All right, so remember this was our mass spring, so we had like a spring, it was stretched. This is x equals 0, and it had some mass on it, and it goes or whatever. Okay, now the orange term there, px prime, what was that supposed to represent? This was our damping, also known as friction. Okay, and the important cases here, there are several important cases here that we need to consider. Basically, p greater than 0, this means that there is a lot of friction and you're going to have damped oscillations, which is exactly like it sounds. Don't worry, we'll make some doodles here, and you can always reference your notes for the older stuff that we did. P less than 0, this is going to be forced oscillation. So something about the material that it's traveling along actually speeds it along. That doesn't make a whole lot of sense with this, but that's the idea behind it. And then p equals 0, we have this sort of undamped oscillations, and so I'm just going to call them pure oscillations. Okay, so that's what the orange term means right there. The red term, well, most specifically q, is our spring constant. It's also sometimes known as the stiffness. All right, if you have a really stiff spring, it wants to pull itself back, but then it builds up a lot of force, so it's going to push itself away really strongly. Okay, and so this is the way we want to start here. We want to think about these things within this context and move forward. Okay, now what's interesting here is if I look at a time series of my displacement off of the rest position for my spring mass. Okay, we're going to pretend that's actually touching the floor. There we go. Haha. And this is x equals 0. So it's stretched out. And this right here, this is our x right there. The distance of our mass from that 0 position. Okay, there's a lot of options that one could have. All right, let's go ahead and make these colors, and then we'll stick to these colors for a while. Okay, you can have sustained oscillation. Okay, where the peak is the same. So this is basically when p equals 0. That's really nice. Okay, we could have oscillations that grow and just keep getting bigger, and this is when p is negative. It's a weird case, but it could happen. Okay, we could have oscillations that damp in size, and this is when p is greater than 0 because we have friction. Okay, I hope this is all seeming relatively familiar to y'all. Okay, and we can have another couple cases which are kind of strange, but basically, let's pretend my initial condition, all these, is not 0. Let's adjust that. Let's put the x-axis right there. We'll erase this bar. There we go. And this is x. So it all, the spring starts at a particular position, and then the oscillations grow or shrink. The last one that I want to talk about is it could just sort of go to rest. Okay, and that's a particularly tricky case. Okay, and so we should discuss that, but for me, this is where the green case there is when P is quite a bit larger than Q. So that basically that friction there is definitely overcoming that sort of spring stiffness in a rapid manner. So it just kind of goes whoop. Okay. So if we think about the orange, it's going side to side, always at the same amount. Okay. The red means it's going side to side, but it's getting bigger and bigger each time. Right, the magenta means it's going side to side by getting smaller each time. And the green just sort of means it goes fit and then stops. It goes rip right there and just stops. Okay. Now, all of these, this is relevant to what we've been studying, I promise. Okay. I'm going to erase this little amazing picture of a spring mass down there. Okay, let's get black back up. Do you remember how to take the second order ODE, like x double prime plus px prime plus qx equals 0, and how to turn it into a system of ODEs? So something like an x prime equals some junk and y prime equals some junk? Well, the trick was to let y equal x prime. All right. Now, if x is my position, this automatically identifies y as my velocity, how fast that mass is moving, right? And then if we took y prime, that's like taking x double prime. So I see this is minus py minus qx. If you don't remember this, like I said, please review. I am going through this bit rather quickly. So I can look at these things, hey, in a phase plane, because what do I have? I have a linear system of first order differential equations. All right. Now I want to draw sort of what's happening in all these cases. Okay. P equals 0. Let's say this is my initial condition for all of them right here. P equals 0 means that I am constantly returning to the exact same position at the exact same speed because I'm moving in a periodic orbit. So I'm on some sort of orbit that comes back to itself. Fantastic. P less than 0 means that I'm driving it away, and so in some sense I'm spiraling outward. And if I trace this all the way back, I could go whoop and just have this spiral working its way outward. Okay. When P is greater than 0, something's dampening my flow. This picture is getting ugly super fast. I know. Which would mean that I'm spiraling in toward the center. Okay, if I want to make that kind of crystal clear here, let's go ahead and X murder that. Ill-fated idea. Let's make 4 different pictures. Okay, great. With orange, we have pure oscillation come back on itself. With red, we're constantly growing outward. We're spiraling outward. With pink, we're spiraling inward. And then with green, no, I don't want that green, I want that green. We're just sort of going flip. Okay, that last case should look familiar to us because this is like a nodal sink. Where it just kind of goes flip. And that matches sort of what we were talking about here with P particularly greater than Q. Okay, so again, I haven't gotten actual calculations. I'm trying to build a cool sense of the shape and geometry and where some of this stuff comes from. Okay, let's rewrite that second order differential equation for the 85th time. The characteristic equation is in the form lambda squared plus p lambda plus q. And now that we're doing all the eigenvalue, eigenvector stuff, you might be like, oh, look, it's the same lambda. Yeah, it is. All right, and so from here, lambda equals negative p plus or minus the square root of p squared minus 4q, all that business over 2. All right, now in the green case, p is much larger than q. And since p is much larger than q, you can actually come up with exactly how much larger it has to be. But then we know that p squared minus 4q is going to be positive. And when that is positive, we have lambda 1 does not equal lambda 2, and they are both real roots, which is exactly the case we did before. Okay, now if we're damping, which means that p is positive, then if I look up here, I've got, let's think about negative p. Negative p is in fact negative. That's pretty easy. Actually, let me note it in a different way because I like doing this. That's a negative term. Okay, now we think about p squared minus 4q. Okay, now since we have a spring restoring force, that means q is positive, which means this number right here is less than p squared, which means this big number right here is less than p. Keeping up with me so far? And so negative p plus or minus a number smaller than it. All of this is negative. Da, 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 da. So you have two real roots that aren't equal to each other. They are both negative. Haha, nodal sink, which exactly matches, I don't know why I just did 2 page at once. Exactly matches this picture here and the time series interpretation up there of just sort of exponentially crashing down. What about these other cases? These other cases are kind of weird, right? P greater than 0, there's a little bit extra here with P is not super huge compared to Q. And we'll discuss what that means, I promise. Okay, P negative and P equals 0. There's a lot to do there, okay? So let's handle this first here. Let's do, crap, I lost track of my colors. All right, let's do P equals 0 first, which is in orange. All right, orange. P equals 0. And don't worry, we'll get to the punchline, okay? So this means that x double prime plus qx equals 0, okay? We know how to solve this. We really do. Lambda squared plus q equals 0, which means lambda equals plus or minus I the square root of q. And so I know my solution, x, looks like c1 cosine of root qt plus c2 sine of root qt. All right? And what's nice is there's no exponential business making that all ugly. So we do indeed have some sort of ellipse where the eccentricity of the ellipse, how much it's stretched out in either direction, is really going to be kind of determined by these constants right there. Okay, but so we've got this nice little, we've got some sort of ellipse there. This is great. We have periodic solutions. Okay, but what does this mean in system land? Okay, so if we are back to thinking about, well, what about our one-dimensional first order systems? We've got x prime equals y. Okay, and y prime equals negative qx. Now, this is just an example. We're doing the simple examples here. So if I define a state vector y, that is going to equal a matrix times my state the derivative is going to equal the matrix A times the state vector y. Now, in this case, y is equivalent to our little x and our little y, and a, is equivalent to 0, 1, negative q, 0. And remember to start off with all this stuff makes sense if q is positive. That's just our special handy-dandy case right now. Okay? I need to find eigenvalues and eigenvectors of this bad boy. Okay? We should get the exact same answers. Let's find out. Okay? So, negative lambda, 1, negative q, negative lambda. I need to take the determinant of this matrix. So I got lambda squared plus q equals 0. Hey, check it out. Lambda equals plus or minus I square root of q. So it's the exact same thing. Thumbs up, everybody. All right, and we understand right now that what's happening here on the xy plane is that I've got these sustained oscillations. That is in this picture, right? Oh, the picture I erased. This means we have sustained oscillations. And so we have something right now. If our roots are complex, if our eigenvalues are complex, they're always in the form alpha plus or minus I beta. What we can tell always is that if alpha equals 0, then the fixed point here at the origin, which is still a fixed point, is called a center, because it's the center around which our oscillations rotate around. So far, so good. This makes sense to y'all? I hope it does, because it only marginally makes sense to me. No, I'm kidding. I get it. All right, next thing is P is negative. All right, so let's do P is negative. In red, E less than 0. All right. Okay, so in this case, my characteristic polynomial is lambda squared plus P lambda plus Q equals 0. And let's go ahead and remember, as always, that Q is positive. Okay, lambda equals negative P plus or minus the square root of P squared minus 4Q all over 2. Okay, now if P is negative, then we've got a positive term plus or minus the square root of, now let's look at P squared minus 4Q. Okay, it depends on the relative size of things, right? Because this could be a real number, and then we've got, oh, 2 positive values. So think about it this way. We've got a case that we've actually already covered, which is where all of that is a positive number divided by 2. This leads to exponential growth. And we have a nodal source. So think about what this means. This means that P squared is bigger than 4Q. Which, what is P again? That is that weird force on the surface that we're moving on that's actually rushing the mass on the end of my spring away from 0, away. And it's much stronger than the spring stiffness. And so basically it just stretches that spring out to infinity and sends the mass off into La La Land. We already understand this case. Go away case. Okay. The other case, which is more realistic in some sense, is that P squared minus 4Q is in fact negative. Okay, which means that my spring stiffness is bounding this sort of slipperiness of the surface by a certain amount. Okay, again, it's hard to imagine something that acts opposite of friction like this is, so you can think of it as some sort of driving force that's dependent on the velocities traveling, but it's not exogenous because it's still a homogeneous differential equation. Okay, sorry, I had a little burps there. But if that's negative, then basically my lambdas are going to be equal to negative P over 2 plus or minus I times the square root. Now, since I've pulled an I out, I have to change the order of what's inside the square root to have that negative 1 that I was able to take the square root of. So now I have got an alpha plus or minus I beta. What's important? Beta, positive number. Fantastic. Alpha, in this case, is also a positive number. right? Because P is negative, so negative P is positive. P is for positive. Now, my solution to this thing from the second order business is C1 e to the alpha t. Why did I put a C1 there? Whatever. Cosine beta t. No, that's fine. Plus C2 e to the alpha t sine of beta t. Okay, and what do we expect? Since alpha is positive, this is driving us away, and this is making us oscillate. So what does this solution look like? I'm doing a lot more erasing than I have in previous videos. I kind of like it. It means that no matter where I start, I go away. This is what's known as a spiral source. Savvy? And what's interesting here is that this right here, this calculation is the exact same on whether this comes from the characteristic polynomial of the second order differential equation or if it comes from solving the determinant of a minus lambda I must equal 0 from the eigenvalue problem. Okay? What's missing here in this setup is we don't have a vector valued solution. While it looks extremely similar, it is in fact not the same. I'm putting off doing the vector valued solutions to the very end so we can see, because it's just big ugly calculations, and some of us already have a handle on that, and I just want to get through some of the geometry of these things. Okay, the last one is P is positive and P is not a whole bunch bigger than Q. Okay, so we're not in the green scenario, we're in the pink scenario. Okay, so what that means, let's get the pink scenario here. P is positive. Whoops. P is positive. P is not a whole bunch bigger than Q. And we need to remember that Q is positive. Okay. So when I take a look at lambda equals negative P plus or minus P squared minus 4Q over 2, like I said, this statement can be made precise. Specifically what I want here, okay, is that it is bigger, but not too much bigger. Okay, or rather, it can be bigger. It doesn't have to be bigger. It can be smaller. I still want P squared minus 4Q to be negative then. All right, in order to try to wrap our heads around that, okay, in the previous problems up here, in the green scenario, P was much larger than Q, ensures P squared minus 4Q is positive. The exact line is P squared needs to be greater than 4Q, or P squared needs to be less than 4Q. These are the statements analogous to much greater than, not much greater than. Okay? I don't like speaking exactly because I like to confuse you guys. Okay. My eigenvalues, exact same as before. 4Q minus P squared all over 2. Except now this term right here is negative, and that term right there is positive. And so now what I can expect is oscillations that decay towards the origin. This is called a spiral sink. Savvy? Okay. Now, what does all of this mean in terms of systems? Okay. What I don't want you to have to do every time you see a system problem like this is to first, I don't want you to do this. Okay. So don't do it. Take the derivative of the, whoops, that's supposed to be an equal sign. I always write plus. Take the derivative of the first equation, sub in the second equation where you see a y prime, that is supposed to be a plus, cx plus dy. Then take my first equation and solve for y in this fashion, and then plug it into here. We've done this before. That's why I'm going fast, because I'm not here to teach it. You can always watch the old videos if you wish to learn it again. Close parentheses. Basically what we'd get is x double prime plus px prime plus qx prime equals 0, where p is equivalent to negative a plus d, there we go, and q is equivalent to AD minus BC. Do we recognize these guys as negative trace and determinant? We should, because we already did this stuff, so we know this stuff supposedly. Okay? I don't want you to have to do this every time. I don't. I want you to work with the matrices. And besides the fact, when you get your solution for x, it's really big, I don't want you to necessarily have to take big, ugly derivatives. Like, take a look at this solution in red right here, okay? So this is what the x looks like. Well, what about my y component? Oh, we'll take a derivative of this. Oh, and by the way, don't mess up. Okay? You're probably going to mess up. I'd mess up. So I don't want to have our fates hanging on that. So we're going to look back at vectors, and we're going to do an example here that I wrote down really nicely on a piece of paper so I wouldn't forget. Okay? I actually don't need to start with that. Don't start with that. Okay. I am still going to start with something like this, just as a side note. This would not be how the problem is stated. So this is official sidebar material. Okay. If this was the second order, then I'd get lambda squared plus 2 lambda plus 2 equals 0, which would give me that lambda equals -1 plus or minus I. Okay. Which means I know my solution for x would equal c1 e to the minus t cosine t plus c2 e to the minus t sine t, and I would get some spiraling decay inward. I would be, in other words, in the pink case. Okay, but this is a sidebar. This is not the problem as stated. So here's the problem as stated. Okay, x prime equals y, because I cheated. Actually, no, let's not do this one. Let's do, I thought I had this written down in a different form. That was less obvious. Oh, my trace has to be -2, and my determinant has to be 2. Okay. My trace has to be -2. And my determinant has to be 2. So that's 1. And then I have to subtract from that -1. Let's go ahead and add there and subtract there. There we go. There's my system. Ha-ha. Okay. Brain parts. And in fact, I did this wrong. There's a 2 right there. Don't call me out. I fixed it. Delete the comment you put on the video. None of you commented on the video. Anyway, here's my system, and I'm going to ask you to classify the stability of the equilibrium 0, 0 and doodle the phase portrait. Okay, that is your task. Okay, so step 1 in doing this is don't make the second order differential equation, solve it, and do it that way. Do the following. Find the coefficient matrix for the system of -1, 1, -1, -1. Okay? Isn't that a beautiful coefficient matrix? Do find its eigenvalues. So we're going to take the determinant of a minus lambda I, which is equivalent to the determinant -1 minus lambda, 1, -1, -1 minus lambda. Okay? Which is equivalent to -1 minus lambda squared plus, plus 1. And this needs to be equal to 0. Okay? That's a nice polynomial that we can solve. All right? So I've got lambda squared. Now, negative lambda times -1 is a lambda. We're going to have 2 of those. Plus 2 lambda. -1 squared is 1, plus 1 is 2. Equals 0. Does this look familiar? Does it look familiar? Because it's the same equation, like it should be. Okay? Working from here, this means that lambda is equivalent to 2 plus or minus the square root of 4 minus 8 all over 2, which is 2 plus or minus the square root of -4 over 2, I'm being pedantic, equals 1 plus or minus the square root of -1 equals 1 plus or minus I. Don't know why I went through all that effort. 1 plus or minus I are our eigenvalues. Now, because I'm looking for vector-valued solutions, I need to compute my eigenvectors. This could be ugly, right? So we're going to just make mental note again of what A is. -1, 1, -1, -1. Okay, so I'm going to write A minus lambda I. So I'm going to rewrite A, but subtracting. Let's go ahead and pick one of these. Let's pick lambda equals 1 minus I. Yeah, I like that one. Okay, -1 minus 1 plus I. 1, -1. And -1 minus 1 plus I. Groovy. Multiply that by some currently unknown vector, and that should be equivalent to my 0 vector, because that's the eigenvalue problem. All right. Oh, it's fine. That's right. I'm doing something different this time. Duh. Okay. So I've got -2 plus I. 1. I'm winging it now. I'm off my notes. It's going to be crazy. Is he going to get it right? Is he going to screw up? I don't know. Pay attention. Call me out. Okay. Now I need to take one of these rows and dot product it with this vector here and set it equal to 0. So I'm going to get -2 plus I times V1 plus V2 equals 0. And that's the only equation that's useful for us. Now take a peek at that. Okay. Identify the ugly part. Make the coefficient in front of the ugly part the number 1. Why? Because you always can. So we're going to set V1 equal to 1. And so what I'm left with in that case is -2 plus I plus V2 should equal 0. That makes selecting V2 really simple. 2 minus I. So we have a complex eigenvalue and we have a complex eigenvector. Now, if you remember all the stuff we did with complex and how the conjugates are essentially the same thing but different, yada, 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 don't bother doing the other eigenvalue. You can, but you don't have to, and we will investigate why. Okay? So, but what this does is it gives me one solution here. Let's call it y1, and it's a vector-valued solution. Okay? It equals c1 e to the lambda 1t v1, just like they all do, except now we've got incredibly ugly things. Is it -1 or 1? Whoops, I pushed up like 6 times. Oh, it's 1 minus I. Okay. 1 minus I, that's an I, t, and then my vector is 1 and 2 minus I. Right? This is complex valued. It's awful as far as interpreting the outcome of a real valued problem. So let's make them real valued. Step 1. Break up the exponential into its constituent parts like that. I've separated out the real part and the complex part. Okay. Now use Euler's identity to rewrite the complex part as sines and cosines. This should feel vaguely and terrifyingly familiar. Cosine of -t plus I sine. Crap, I ran out of room. Rewrite. Let's try to write small this time. C1 e to the t. Go ahead and put it right here. Cosine -t plus I sine of -t. Close that parenthesis. Multiply by the vector 1, 2 minus I. So far, so good? Okay, great. Now what I'd like to do is I want to write this as 2 vectors. Okay, let's call these vectors VR plus I VC. I think you can guess. I want VR to be a vector of all the real parts of this solution. And then I want VC, all the elements in it are going to be real. But since it's multiplied by IVC captures all the imaginary parts of this solution. Okay. So breaking this up, I'm going to take this term and multiply it by both the top and the bottom. Now I can do that out in excruciating detail, or we can kind of go along with me on a little ride. Okay. Cosine plus times 1 is real. Okay. Cosine times 2 is real. I sine times negative I is real. Those are all of our real parts. Okay, I don't need, go ahead and adjust your notes if you're taking them. Just get rid of the C one. We don't need that. Holy shit, that got rid of a lot. E to the T. There we go. Okay, so to write this as a vector, cosine times the 1. Cosine minus T. There is nobody else in the top spot that produces real values. Oh, cosine times the 2. 2 cosine of negative T goes in the bottom. I sine of negative T times negative I is 1 plus sine negative T. All of this is multiplied by e to the T. Let's go ahead and put it in the beginning. And then we're going to add to that I times VC. So this right here is my VR. So far, so good. To follow those exact similar lines there, woohoo! Cosine times the I is complex. I sine times the 1 is complex. I sine times the 2 is complex. So let's put that together to make our VC, shall we? Right, equals. I'm just going to rewrite VR here. We know what it is now, but it's okay. In the top spot is sine negative T, because we see the I's on the outside, so I don't have to rewrite it constantly. And then the bottom is 2 sine negative T minus cosine negative T. And this right here is my VC. Now, the book is going to go over a lot of details that I don't really have to go over here. I think y'all are pretty bright. But if Y1, if we're able to write it as VR plus IVC is a solution, then VR and VC all by themselves are solutions. Therefore, the general solution to the problem is C1 VR plus C2 VC. Okay, so coming up here, my original problem was this guy right here. Okay, which means I can write its solution as C1 times this vector plus C2 times that vector. Cool, I have the solution. That's pretty awesome, Pilgrim. I forgot the E to the T right there. Bye-bye. Okay. Oh, that seems like a whole bunch of work. Yes, but we also need to classify the stability of the origin. Well, it's complex with real part positive. We look at my solutions, they all have these e to the t's, which is growing. So the origin there is an unstable spiral. Excuse me. Like we said before. I ate popcorn earlier, and a little popcorn shell just went in my throat. I'm slowly dying. It was been fun teaching all of you. Hot damn. To summarize all of our results so far, let's go all the way back to page 1 of the notes. Okay? Okay. Now, if the lambda 1 and lambda 2 are both real, okay, if and not equal to 0, if they are positive, then it's an unstable node. right? If they were both negative, it was a stable node. Okay. If one was positive and one was negative, we called that a saddle node. Okay. In complex land, we have a couple different cases here. If alpha equals 0, we call that a center because we have purely periodic solutions. If alpha was negative, we had a spiral sink because they spiraled in towards the origin. And if alpha is positive, we had a spiral source because it spiraled outward as it grew up to infinity. We have what the book calls and reserves as special cases. And it groups, whoops, not what I meant to do, undo. It groups them all together. So this guy and these two homies right there. Okay. Repeated eigenvalues and when eigenvalues are equivalent to 0. We will cover those in the next talk, in the next video here. And then we're going to summarize a lot of these lessons that we've learned into something called the trace determinant plane. Okay. Yeah, I think that's everything I wanted to tell you guys. Yeah, may the force be with you. How many of you Catholics said, and also with you?